I'd like to do some examples that come off of page 477 of our textbook. The first 4 problems I want to do come from this section where we're instructed to use properties of logarithms to expand each logarithmic expression as much as possible. Where possible, evaluate logarithmic expressions without using a calculator. So I want to do problems 14, 37, 38, and 40 from that section. And here they are, and I've shortened those instructions to expand. We can also think of this as rewriting these logarithms as a sum or difference of logarithms. Well, to start off here, I have the natural log of e to the 4th over 8 in problem 14. And so I'm going to use the difference rule for the logarithm. So I have the natural log of the top minus the natural log of the bottom. I can pull that 4 out front. And we all know the natural log of e is 1, so I can just write 4 there. So that's 4 minus the natural log of 8. At this moment, I could have also remembered that the log base b of b raised to a power is just the power, one of our properties of logarithms from earlier in the semester. When I'm expanding logarithms, I get kind of focused in on writing powers out front, and the log base e of e is 1, so we get the same answer anyway. This is a good final answer, and I don't have to do anything else. I suppose if I really was looking for something else to do, I could remember that 8 is 2 to the 3rd, and then rewrite this as 4 minus 3 times the natural log of 2. That's not necessary, but we could do it if we were so inclined. Next up in number 37, I'm asked to expand this logarithm, the natural log of x cubed times the square root of x squared plus 1, all over x plus 1 to the 4th. Well, let's see. On the top, I know I'd be looking at this. I'm going to rethink that square root as a 1/2 exponent. And then I'm dividing by x plus 1 to the 4th, so that would be minus the natural log of x plus 1 to the 4th. And then my final step, I'll pull all those exponents out front using the power rule for the logarithm. All right, and there's number 37. Number 38 looks a lot like that one, and I'm going to in fact try to show even less work this time. Now you can show as much or as little work on expanding these as you feel comfortable with, but I'm going to try to go from the way this one is written to a final answer. Just going on thinking about that square root as a 1/2 power. And there's a nice final answer. I'm going to clean up that parenthesis just a little bit. All right, and then finally, in number 40, the log base 10 of all this stuff, 100 times x cubed times the cube root. And if you look in the text, that's written very neatly, but that's a cube root there in number 40. Let me see if I can make that look a little nicer for the video. All right, and again, I want to try to treat it like this one, where I write as little as possible, try to do this as efficiently as I can. So let's see, I have the log of 100 plus 3 times the log of x plus 1/3 the log of 5 minus x. I have 1, 2, 3 things being multiplied together on top, so I have 1, 2, 3 positive logarithms being added together in my final answer. On the bottom, I need to subtract the log base 10 of 3 and 2 times the log base 10 of x plus 7. And I would like to write that right there, but didn't quite have enough room, so I'll just kind of do it that way. And then finally, on this one, if I look at the log base 10 of 100, well, what power do I raise 10 to get 100? Well, 2. So the log base 10 of 100 is 2. And so I get to evaluate that and simplify my final answer just a little bit more. All right, so that gets us through the first 4 problems that I wanted to do off of page 477, the ones where I was asked to expand a logarithm. The next 4 problems come from a section of the book where instead of expanding, we're asked to condense logarithms. And the instructions here at the bottom of page 477. Use properties of logarithms to condense each logarithmic expression. Write the expression as a single logarithm whose coefficient is 1. Where possible, evaluate logarithmic expressions without using a calculator. So the problems in that section I wanted to do are problems 50, 62, 66, and 70, and here they are. And so this is going the opposite direction from how we were just working through the problems. Instead of expanding the logarithms, we're going to condense them into one logarithmic expression. Well, the first thing I do is think about any coefficients like this 7 as actually being an exponent, so it'd be a y to the 7th. And then I can rewrite that as log base 10 of x times y to the 7th. And again, we can hop right down to that final answer. You can show as little work as you feel comfortable with on one of these. So let's see if I can shorten the amount of work I show here in number 62. So I have the natural log of x to the 4th times y to the 7th all over z to the 3rd. In number 66, there are actually a couple different ways we could go about the problem. The way I want to think about doing is I'm actually going to distribute this 1/3 through. And so now I can think of it as a cube root on both of x and y, or a 1/3 power on both of them. So let's see. Oh, no bottom here. Those are all, now I see. Wasn't paying attention. I have two positive logarithms and one negative. So I do need the fraction bar, but this actually goes on the bottom. So that would be a y to the 1/3. I'm going to write it as a cube root. On the top, I have the cube root of x, and then multiplied to the cube root of x, I would have x plus 1 squared. All right. One more example from this set of problems, and again, I'm just condensing a logarithm. So another problem that's a log base 10. I have two negative logs and two positive logs, so I'll have two factors on the top. I'd have an x and an x squared minus 4. And on the bottom, I'd have a 15 and an x plus 2. And there are 4 examples where we get to condense logarithms. The next 4 problems I'd like to take a look at, 3 of them come from this section, where the instructions in the book ask us to use common logarithms or natural logarithms in a calculator to evaluate these to 4 decimal places. And then this one down here, number 82, where I'm asked to graph using a graphing utility. So let's start with those. So the way I actually like to think about doing these first 3 is instead of the instructions being to use the natural log or common log, I would like to say use the change of base property to do it. Because that's how we would get to use the natural log or the common log. So change of base tells me that this could be the common log of 17 over the common log of 6. Or you could choose to use the natural log of 17 over the natural log of 6. Same 2 options here, log of 19 over the log of 0.3, or the natural log of 19 over the natural log of 0.3. In 78, we have the same 2 options. So the log of 400 over the log of pi, and that's going to be the same thing as the natural log of 400 over the natural log of pi. Now let's use our graphing calculator to evaluate each one of those. I'm going to use the common log on this one just so we see one example of doing that. It does not matter. So I have the log of 17 divided by the log of 6. And that gives me 1.5812. On this one, I'll use the natural log. So the natural log of 19 divided by the natural log of 0.3. And I get minus 2.4456. Now on this one, I'm going to stick with using the natural log because that's what I would typically do anyway. So the natural log of 400 divided by the natural log of pi. And I hit enter too many times. Unfortunately, I just did the same calculation again because that's what to do. And so this one I have to be careful because when I look to 4 decimal places, that would round up, and so it actually gets me to be 2.340. All right, and that's how we use the change of base property, common logs and natural logs to evaluate logarithmic expressions. In this last problem, we were asked to graph, also using that same idea. Graph this in a graphing utility by using the change of base property. So I'm going to do that in a minute. But since we've learned how to graph these by hand, I thought I would graph it by hand first, because I always think that's a good thing to review. And so I know what the graph of a logarithm looks like when the base is larger than 1, right? They have an x-intercept at 1 and grow like that, have a vertical asymptote with an x minus 2 in there. Everything's going to be moved to the right 2 units. All right, well, I usually like to plug in x's so that I get out what the base is. On the inside, I plug in the base, I plug in 1, and I plug in the reciprocal. So I want to think about what that would be. I want to have 3 on the inside of the logarithm, which means I'll actually have to plug in a 5. Okay, so I'd usually put a 3 in the table. It's moved to the right 2 units, so instead of being at 3, now it's at 5. I'd usually plug in a 1, and if I slide that to the right 2 units, that's going to be at 3. And I'd plug in a 1, and it's going to move to the, excuse me, I already did that. Plug in a 1/3, the reciprocal of the base, move that to the right 2 units. That's going to be at 2 and 1/3, or just 7/3. So those are the x values I want to think about plugging in. Plug in a 5. 5 minus 2 is 3. The log base 3 of 3 is 1. Plug in a 3, and we get a 1 in there. 3 minus 2 is 1. The log base 3 of 1 is 0. Plug in that 7/3 and take 6/3 away, you get 1/3, and the log base 3 of 1/3 is minus 1. All right, 1, 2, 3, 4, 5, 6, 7, minus 1 and positive 1. Let's see what this graph looks like just plotting these 3 points. At 5, I go up to 1. At 3, I'm on the x-axis. And at 7/3, 2 and 1/3, I go down to minus 1. Vertical asymptote is now at 2. And there's my nice, happy logarithmic function. All right, so we graphed it by hand, but the instructions were to actually use a graphing utility. So type in this, the natural log of x minus 2 divided by the natural log of 3. I'm going to hit zoom 6. This is what the calculator screen normally looks like. And I see the calculator is having a hard time showing what happens at this vertical asymptote, and that's why graphing it by hand is actually a little bit better for us. I'm going to hit the window button and change the viewing rectangle. I'm going to have it do what I'm looking at here. All right, and on the y-axis, just from minus 2 to 2. Now I see a graph that looks a little bit more like this, and the calculator is not having as much trouble. All right, well, those are the examples for this week. That's it for now.